So my name is Tang, and I'm from Department of Computer Science of Tsinghua. And my research interests mainly include social networks and also data mining and also machine learning. And I have been visiting scholar at Cornell University and blah, 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 blah. Anyway, I have published some paper on data mining and also machine learning and also some other field. And also I want to introduce a bit about our lab. So I'm from knowledge engineering group of computer science. And also in Tsinghua, actually we build some kind of, today my talk will be about our system AMiner and toward understanding bigger scholar data. And in Tsinghua, actually we in particular build some kind of center we call the Big Scientific Research Center for data science. And also this center actually is under the Data Science Institute. The dean of the Data Science Institute is Philip Yu. Okay, and also we have another center working on social network analysis, that is interdisciplinary social network research center. We have some collaborators from psychology and also sociology and also some other different fields anyway. So that is our research collaboration and research center in Tsinghua. Well, today I will mainly focus on, the system, AMiner system. Originally we called it AMiner, but it's really difficult to remember this name, so we just changed the name to AMiner, so it's really to understand. So if you want to short it again, so it's like AM, that's morning, right? So what is AMiner? So basically AMiner is an author-centric academic search and mining system. So if you go to AMiner system and type some kind of query, and you will find, for example, here is data mining. And if you search data mining, and you will find experts on data mining. And also you can check the similar author, or for example, if you are interested in Jiawei Han or Philip Yu, you can check the similar authors or something like that. And the more interesting is that we collect the query and we understand the intention of the user search, so that we can collect the query with some kind of knowledge concept. For example, the data mining, we automatically collect the data mining concept to concept in Wikipedia. And also we have automatically extracted the demographics of authors, for example, gender and language and location. So this is very important. For example, you can answer some kind of very difficult question. For example, if you want to find some kind of female researcher work on data mining and located in United States, and then you can find such kind of experts. So if you just click one expert, you will see very detailed information. For example, this is the profile of each researcher, and then you can see the basic information and also research interest, and also you will find that it will automatically collect the publication information and also some other information. And based on this information, we can do some kind of statistics, for example, citation statistics. And also we collected some other information, for example, the video lecture. And for example, this time actually all the SM paper and the speaker will be recorded by video lecture. So we can automatically collect the talk information with the author information. And also we collected patent information and also LinkedIn information and also some other information. And so based on this, we can do a lot of things. For example, just give you a very simple example, because this year, since 2016, and we want to release some kind of new feature that is, we want to publish some kind of thing like most influential scholar in different fields. For example, this is the most influential scholar in data mining. And if you go to the website, and you will see we have some kind of different fields in computer science and in data mining, and you will see, and this list is only, we have different metrics. So this metrics is only in terms of the citation number of the paper published on KDD. So if you go to this data mining, and you will see that the most cited or top cited authors is in KDD. Well, so until now, the AMiner system already connected more than 100 million research profiles and also more than 200 million publication papers. And the system just attracted more than 300 million requests from all the countries in the world, almost all the countries. So this is a user distribution, for example, okay? So you will see that we have more than 80 million in the unique IP, I mean, from the 220 countries and ranges. This is the top 10 countries. United States is the number 1, and followed by China and Germany and India and also some other countries. So I just first give some high-level introduction about the system. So I will go to some techniques about the system. So firstly, I have to say that the unique goal of the system is that to populate a semantic-based profile system. Okay, so how to do that? We have 3 steps. Okay, the first step is to extract semantic information from the web. And the second step is to integrate information, I mean semantic information from different sources. And the third step is to mining deep knowledge from we already extract some information, and we want to mine the deep knowledge from the extracted information. So let me first introduce the first step, extraction. So basically the problem is very simple. So we have we have web page, for example, my home page. So, so if you go to some home page, and basically we want to extract some structured information. So this is the traditional information extraction, and we published many papers on this topic, I mean, in the past 10 years. And we also need to integrate some information. For example, the paper publication information. Like this is Rudy Body and published native papers on the DBLP and also some other field. And one straightforward question is that how to integrate publication information into this profile. For example, you will see that in DBLP, for example, one researcher published native papers, but those papers actually is not just one author. Probably, I mean, one author with the same name, but it probably belongs to many authors with the same name. For example, this is the papers published by Jin Zhang. Actually, we have another example here. That is Wei Wang. Wei Wang is a popular name in. Okay.
I wish you used my name as the example, right? So
Yeah, that's. No, but No, your example is perfect because we already manually correct your case. Okay, so yeah, so it doesn't make any sense, but you know this is a general case. I mean, yeah. Anyway, so if you check Jin Zhang, actually this is 2007, and you will see that Jin Zhang published. I mean, this name published less than 100 papers, but it belongs to more than 20 Jin Zhang from different universities. So the problem actually is how to assign the paper to the different Jin Zhang. But I guess that you will say it's very easy because we have the affiliation information on each paper, so we can do the assignment, right? So I have to answer your first question. So the challenge is that even 3-year graduate from our lab, okay? So it's really challenging to only use the affiliation information. And you probably will say, okay, I will use another information, that is causal information. We can use the causal information to disambiguate this problem, right? And this is another challenge. You will say, okay, this is one paper we published. I have 2 collaborators, two Yang from different affiliations. So it's really, really challenging. So basically, I have to say, this problem is the challenge is how to perform the assignment automatically and also how to estimate the person number. So I just quickly go through our approach picture. So basically we use the Markov random field. So we have 2 Markov random field, and the first one is a tree structure condition random field, and the second one is some kind of hidden Markov random field. And basically we use the first condition random field for the researcher profiling because the web page is tree structured. So we just use the tree structure condition random field to best model the web page. And then for this name disambiguation, we use a hidden Markov random field. And the advantage of this model is that it is totally unsupervised, and also we can incorporate some kind of semi-supervised information. For example, the user give us some feedback, like we published some paper together with Philip Yu to work on some kind of, we call it interactive name disambiguation. Okay, so based on those approach, we extracted more than 1 million research profiles. I mean, accurately extracted more than 100 research profiles from the web. So this is a constructed researcher database. And probably you will say, okay, it's already enough, but I have to say it's far from enough, okay? So there are still many challenges. For example, the first challenge is that there are still some errors on the web page. Like many people just move. They just move to different affiliations, different companies, and they will change. They will update their web page. And probably you probably find some kind of mistaken web page and extract mistaken or out of the data information. And so in this case, actually, this error will be propagated to the second step, like integration, and also third step, right? And also the second one is that the extracting information is not enough. Like, okay, like this example, okay, you will see this is generative 1. If you check her information, you will find her information actually is distributed on the web in different sources. For example, LinkedIn, homepage, and Wikipedia, and also some other sources. So the problem actually now is become how to integrate the semantic information from the different sources on the web page, on the web. Okay, so we call this problem as integrating semantics across different networks because, okay, so we have different networks like Google Scholar even. Okay, Google Scholar is not just not disconnected network. It is actually a collective networks, like author collective with each other. And also we have LinkedIn, and also we have AMiner. So the problem is how to collect the different networks together. So basically, we could consider local information. For example, the profile information, like how many papers published by each author. And also we can leverage the network information. For example, the similarity of two authors can be propagated to some other, to the peer pair, right? So we can do some propagation. And then most challenging things actually here is how to guarantee the global consistency. Okay, because if you find some similarity or matching between the two networks, and you find some matching between the two networks, and also you find some matching between those networks, but to guarantee the consistency among all the three networks actually is an NP hard problem. So we give some solution, we call it COSNET, and we also collaborate with Jianpei and Philip on this work. And so I don't want to get into the technical detail, but if you are interested, you can check our paper. I just give you some results. So basically, this, for example, okay, we just generated some results like this profile. We automatically collect Google Scholar and LinkedIn and the video lecture and the patent data. So, and it's still not enough because we just do the extraction and the integration, and also we want to do some mining from the information extracted into our database. The first mining task actually is how to understand how to extract the research interest. This problem is, probably you will say this problem is somehow old, and the straightforward method is to extract the high frequency terms like as expertise, as interest. But I have to say that this idea is not so good. Okay, if you directly do that, you will find that you just extract many bad words, like for example, algorithms and the experiments and the data set. Those words are very high frequent, but it's not so good. It's not so good. So our idea here is that, okay, we propose a method called knowledge-driven semantic mining. Okay, the basic idea is that we have some kind of data source like papers or patents, and also we have some kind of knowledge structure. For example, the knowledge structure from the Wikipedia and also knowledge structure from Freebase or Yahoo. And then we just combine the two things together to generate the research interest. And we use a deep learning embedding-based method. So the idea is that we do some embedding for the knowledge concept, use the Wikipedia data. And also we use a network-based embedding for each author. I mean, the author network, we have a network, and then we can do some network embedding. And then we just combine the two things together. Okay. And again, you probably ask how to combine the two things. Okay. So alpha beta combining is not so good. So we propose we call it the gem vector. That is an idea to bridge the research network and the knowledge graph. So basically, it's a Bayesian model to combine the two embedding results. So this is the knowledge embedding results, and this is user network or author network embedding results. And then we use a Bayesian model to collect the two embedding results. And this is a Gaussian distribution. Okay. So finally, we use this method to generate a very good result for the research interest. So this basically is, interest we identify for each expert. So it's still not enough because we are dealing with the author network. We have a network, right? We want to manage some kind of deep semantics for the network itself. So one example is that how to find, for example, originally we have only a black-white. We called it black-white because this information is only, there is no any semantic on the cursor information. There is only cursor information, right? And we proposed a method, actually this work was collaborative with Java. And the idea is very simple. We just automatically generate who are advisor and who are advisee. That is, we identify the advisor-advisor relationship from the network. So the approach actually is again a semi-supervised learning. That is a partially labeled pairwise factor graph model. So we propose this idea, and the idea is that, okay, we have some labeled data, but it's really limited. So we can define some kind of local feature, and also define some kind of features on the correlation feature, and also we have some global constraint and somehow like that, and we have some kind of global optimization for this problem, and the Finder can generate the predicted the labeling information for the results. So this is some kind of results you can see, and basically the yellow one is the advisee of the center author, and the green one is the co-author, some other collaborators or something like that. Okay, so I just quickly go through the techniques in the AMiner system, and probably you will say why I will like AMiner system. So I give you some example. Okay, so you can use the AMiner system to find the collaborators and applying for PhD, and also, if you are senior, you can use the system to find the proposal or paper review, or do some kind of, if you are a company, and you can use the system to find employees. Okay, so this is the first example. So basically, if you are a junior, okay, if you start to working on some kind of new topic, or if you brainstorming for some novel idea, I guess the first question is not to find the papers so far, because if you Google and you will find the data mining, there are just millions of papers on data mining, and you have no idea about which one is good, which one is bad. But I guess the first question you want to know is who are expert in this field, and what are the top conference, and what are the best paper, and what are the top research lab. And because if you have such information, you can follow them, right? And the second question, actually, if you already working on, for example, on data mining for some time, and basically you want to extend your collaboration circle, and for example, if you want to work on some people from the server, and who are the best collaborator for you. So that is collaboration recommendation. And also, actually, we have more challenge question. We can answer more challenge questions. For example, like, okay, this is a real example, okay. This is from National Science Foundation of China, and they really want to find some kind of researcher from United States who can speak Chinese, because our proposal is in Chinese. Okay, they want to send the proposal to some senior researcher in United States to help review the proposal. And also the companies can use the system to recruit female researcher working on, for example, on different topics. And also we can use the system to generate reviewers, for example, for paper. And if you are editor of a journal or conference chair, PC chair, and you can use system to help do that. Okay, probably you will say, okay, that is only your idea. It's not true, right? So I give you some real example, okay? So the first example is that, okay, we just work with MOST. MOST is the Ministry of Science and Technology of People's Republic of China. It's somehow like NIH in United States. The funding is much larger even than than NIH. So we work with them to help them identify experts in different research fields. Actually, this year, all the proposals will be reviewed by experts recommended by us. But I have no idea about who are experts, but we just help develop the system to help them recommend the experts. And also, we deploy a system in National Science Foundation of China. It's an NSF of China, and we help them recommend the experts for proposal review. And also, we integrated our system with Scholar One, for example here. And we have a tool actually for ACM transaction of unknowledge discovery from data. And if you are editor here, and actually you can use this tool, you can download this tool from Chrome store, and then you look at this paper, and the system, the tool will automatically recommend you some kind of reviewers. And you can simply click here, the select, and then all the information are filled into the Scholar One system, and then you just click add him or add her as a reviewer. That's just that simple. Okay, so I have to say that we already have the system, and but we are still very open. Okay, so we want to build a very open big Scholar data and also very open society for the Scholar data mining. So actually collaborate with Microsoft and also many other collaborators from universities and also from different companies. We just build, we call it academic society in the world. And so we want to build some kind of open platform and build some kind of open big Scholar data and also build some kind of open society, not just like for example, Google Scholar, okay? Because Google Scholar is always somehow, they do not want to share any data for research because they cannot do that. So we just share a native data here. And if you are interested, you can go to aminer.org and search data. And you can find the different data. And most of the data actually have labeled information. So you can use those data for research. So, and in particular, actually, we have some unique data. For example, advisor-advisor relationship that is labeled by Mario, and also we have research profile data and the expert finding data, and also many other data. So you can go to the website to check all the data. Well, I'm going to summarize my talk. So basically, in this talk, I just introduce our system, AMiner, and this system is going to, our mission is to understand the big Scholar data, and so that we can really understand what we have done in the past, years or 100 years in academic field. And so based on the semantics, the goal is to extract the semantic information, and also we want to build some kind of social platform and build some kind of open platforms for this field, for the big Scholar mining field. And I want to thank to our partners from Microsoft and Notre Dame. And Notre Dame helps us build a mirror in United States. That's the reason actually if you go to our website, you will find it's very faster, even faster than China. And so we have a mirror in US. And I want to thank you, Erwin King and his very guide team, and also SM and also Semantic Scholar, because SM just share all the publication data with us, and also Semantic Scholar will build some kind of correlation. And also finally, I want to say thanks to our team, and this is many our students and full-time employees, and also our collaborators, Javi and Philip and Jen and many others. So thank you very much.